With experience as a beamline scientist at the synchrotron in Trieste, Italy, and a postdoctoral research at Flinders University in South Australia, he understands and educates on how to make science work for business. Please welcome ANSTO's commercial technology consultant, Dr. Robert Akers. Yeah, here he is. He's going off.
Thanks, Mike. Okay, thanks everyone for coming out today. My name's Rob Akers. I'm from ANSTO, that's Australia's Nuclear Science Technology Organisation. What I'm talking about today is how we can use the capability and expertise at ANSTO that we've developed in the nuclear science space for helping Australian manufacturers solve some of their problems. So we'll start off with a little bit about ANSTO. So we just recently had our 70th anniversary last year, so established in 1953, and our comms team put together this very short video highlighting some of our achievements. So let's just let that run for a second. Okay, so that just gives you a little bit of a flavour of some of our highlights over the last 70 years. Some of the more recent things that we're getting some attention for is you may have heard last year about the little bit of radioactive material that went missing out in Western Australia that everyone was very desperate to find. And it turns out that our team from the Chorus 360 detector development team went out there and drove around with a Land Rover for a little bit and managed to find this tiny thing the size of a grain of rice in the vastness of Western Australia, using our understanding and expertise with radiation technologies. We also saw there that they highlighted our production of nuclear medicine for Australia. So the stat that they like to trot out for that is that 1 in every 2 Australians will know somebody or be somebody who has been the recipient of treatment that's been through ANSTO. So all good reasons to make sure that we have the nuclear expertise here in Australia. So what are we essentially? We're a Commonwealth-funded research organisation, and we operate some of Australia's largest research infrastructure. So some examples of that are the Opal Research Reactor here in New South Wales up at Lucas Heights. So this is the reactor that produces neutrons for producing nuclear medicine, for passing out into the Centre for Neutron Scattering to do materials analysis. We irradiate silicon in that reactor to produce very high quality semiconductors for very specified and high-tech industries. Australian Centre for Neutron Scattering is where we perform a lot of materials research that I'll be talking about today. So that by looking at the way that neutrons interact with material, we can tell various things about the material itself. So where's the strain going in your welds? What's the microstructure like in the material? Do we have massive voids inside the sample? I've got a couple of examples we'll go through in a minute. Now, a corollary to that is down in Melbourne, where I sit most of the time, is the Australian synchrotron. Now, this is a large particle accelerator that accelerates electrons around very close to the speed of light to produce high-intensity X-rays, which we, again, use for a lot of material science applications. So not just doing your chest X-rays like you have at the doctor, we can bounce the X-rays off of samples and materials to look at their properties. So the chemistry, the structure, or again, doing imaging work. We've also got the Centre for Accelerator Science up in Lucas Heights. So this uses ion beams to do, again, materials analysis and materials modification. And we have a bunch of other science facilities, including our Gatry irradiation facility, which is used for sterilization of materials with gamma rays. But we've also been using that for some space radiation testing applications. My team is focused on industry engagement for our nuclear science and technology sector. Now, the way we approach the market is we have at the moment 5 priority research sectors, that being Australia, advanced manufacturing, defence and space, health, energy and resources, and the environment. And what we look at is what are the needs of the industry, so talking to you guys about what your problems are and the challenges that you face in your businesses. And then we also understand what's going on behind the fence at ANSTO. So what are we good at? What capability do we bring to the table? Where those overlap, that's where we figure out, okay, this is the value proposition that we've got that we can deliver to Australian manufacturers, to Australian industry, to add value and solve problems. So the government very keen on using publicly funded research infrastructure to actually help the economy and help you guys solve the problems that you face in your businesses. One example of that is using our neutron and synchrotron computed tomography. I worked with a company based out of Geelong in Victoria called Conflux Technologies. Now they produce very high-end heat exchangers for applications in oil and gas, high-end racing vehicles, space applications, anything where you need to move heat around in high efficiency. So they're printing these very complex structures in various metals. So these ones would happen to be aluminium based. Now because the internal structure is so complex, you've got to make sure that what you're printing is actually what you think you're printing. So where they came to us to do some non-destructive testing using our computed tomography setup. So this is like when you go into the doctor and in the hospital and you've got a bad knee, they put you in the big donut and you get the big scan done to show the internal structure of what's happening in your bones. We're doing the same thing with our X-rays and neutrons to look at where are the defects happening in these materials? What's the microstructure look at? Do you have any entrained powder after you print? So we were able to help them look at where the points of failure were in their builds and relate that back to the process variables they were using at the time, so they can twiddle the knobs a bit differently on the machine and eliminate those errors from the print process and give them a reliable product. So one case we had was they had an export job during the COVID lockdown that was being held up by a quality issue. The only way they could solve that issue was coming to the synchrotron and scanning these parts, and we were able to help them quickly identify the problem and resolve it so they could get that export job out the door, save them some time and money, which is very critical, especially when we were having the supply chain issues that we saw during the pandemic. Another additively manufactured metal part is looking at these rocket nozzles that were produced by a company called SPE3D. Now, they have a couple of sites around Australia. They're based out of Darwin. They've got some manufacturing also out in Dandenong in Victoria. What we were looking at here is where's the residual stress in their parts. Now, residual stress is very important in a part because if you're building up too much stress, then this can lead to cracking and failure of the part. Now, if you're strapping these things to a big rocket and getting all these vibrations that you experience during launch and you're getting cracking and failure apart, that can be a very bad thing. So by visualizing the stresses in the part using our neutron strain scanning, we're able to help them understand the way that they're designed and the treatment of the part results in different stresses and how they can be alleviated either with changing the design, the shape, the build parameters, or by post-production heat treatment to resolve those stresses. Now, it's not just on additive parts that we can do this. So we've also done this with fairly large engineering structural parts. So that piece that you see there in the middle, that's a piece of gas pipeline section where we're looking at residual stresses on some weld segments. We can also look at simulations of the material using finite element analysis that uses the output from these scans to inform the model you're using in the computer, so you can use that in your design specifications and when you're looking at designing new parts with the particular materials. So we're actually taking the real physical measurements, feeding them back into the model, so you're not just guessing or picking a number out of an old CRC manual or engineering manual. We can actually directly measure these things so that you've got high confidence of what's going on in your computer model. But what happens when you've got defects in the structures that you just can't resolve by changing your build parameters? And ANSTO has a long experience in a process called hot isostatic pressing. Now this is where you take high temperature furnace with a high pressure of gas that's pushing on a part equally on all sides to do a heat treatment. So what's happening here is you can refine the microstructure and reduce voids and cracks in a part by applying this pressure equally across all the part at critical temperatures. So this is an example we were doing with a company called Titomic out of Clayton in Victoria. They were producing printed titanium fuel tanks for space applications. And you can see in the top structure here on that micrograph, there was the as-built part was, after their heat treatment, still had some very large voids present in the structure. Now again, these are bad because they can open up and become crack initiators, and you see failure of the part under vibrational stresses or impact. There's a huge difference after our team did the hot isostatic pressing. You can see that those voids are almost completely closed up. There's only very small, isolated, very small voids throughout the part after that. This is also resulting in improved part performance. So this is things like ductility or stretchability or hardness. So lots of the engineering properties that you're looking for that are critical to your builds can be improved by this process. Another job that we did with the Titomic guys were looking at shielding material that they were designing to protect sensitive electronics in satellites in orbit. So it's quite a harsh environment up in low Earth orbit or in higher orbits. So there's a lot of radiation flying around, and this can trigger what's called bit flips or other types of failures in sensitive electronics that are on these chips. If you've have that happen in a mission critical part, then guess what? Your satellite might be stuffed. We saw from what happened with Hubble that it's not exactly easy to go up and service these things in flight. So what people are looking at doing is testing their electronics for space environment before they're sent out, so they can understand, okay, how susceptible are we to space radiation? What's going to happen if we do have one of these events occur? And they're also looking at shielding material to prevent these radiation effects on the sensitive electronics. The way Titomic were doing this they were printing what they were calling Z-graded material. So this is basically saying at different heights on the sample, you've got different thicknesses of different materials. So they're building those using their 3D printing technology so that, okay, you've got X thickness of one material and then Y thickness of another. The big question there is, how thick should each layer be? What order should they be in? To figure this out by using empirical methods, so printing a bunch of stuff and testing it out, that gets very expensive and time consuming. So the team at ANSTO, because of the way we understand how radiation and matter interact, were able to help them with some simulations to narrow down the candidates for testing. And then they printed a smaller subset of test parts based on those parameters, and we used our gamma irradiation facility to actually test them and validate those simulations. This helped them reduce their commercialization pathway significantly and got these parts actually onto the spacecraft and launched quite quickly in the end. One that's a little bit different, this is an example I've been using for quite a while, so my boss is always like, why do you keep using that one? Why don't you find something fresh? But this is a great example of some of the science that we do because it's visual and it can be understood. So this is a comparative study for a company called LaserBond who do laser cladding of large engineering parts, so like your big cutting tools on mine sites or big machinery. So when the cutting teeth wear out, you don't necessarily want to throw the whole part away and get a new one. You can resurface and reharden using this their technique. Now they came up with a new technique of doing this laser bonding that they knew was giving them superior performance compared to the old method, but they couldn't exactly explain why. And so they brought it to us, a couple of examples of each process, and we're able to show them that On the left-hand side there, that's the old process. So what's going on with the colors here is the red, that's the iron in the steel of the original tool, and then you've got the nickel tungsten layer of the hardened surface underneath. You can see in the old process that you're getting the iron mixing with that layer. So you've got these fingers of iron coming into the hardened surface layer. Now this is causing some weak spots and some poor wear characteristics. But with the new process, you can see that it's nice, clear boundary between the two layers. So the hardened layer is just the nickel and tungsten. Great thing about this is you don't have to be a scientist to understand what's happening in that picture. So they actually included these images as part of their report to the ASX, and maybe it helped their profitability a bit. But it's something that the executives found very useful as part of communicating about their new process and how good it was. And we've even got a quote there from the executive director about how great it was. So this is all great, Rob, but how do I come and use ANSTO to solve my problem? So there's a few different ways that you can come and use the capabilities at ANSTO. Most of the work that goes through ANSTO is through the merit system. So this is academics at universities applying for time just like you apply for a grant. So there's a couple of rounds a year, depending on which application and which process you're looking at. But it's a matter of, this is my science case for what I want to do. These are the merits of it. A panel of experts, external experts, look at that, give it a scientific ranking. We've got X number of weeks of time available when they allocate Y number of proposals. This many get through, this many get cut. Fairly standard process. Part of that is that if you go through that scheme, you must publish the work in peer-reviewed journals. There's no IP protection using the merit access scheme. So we want to be able to talk about it. Like it's publicly funded so that we can get the science out there and generate the knowledge for people to use. Now for our commercial clients, this isn't always desirable either because of time frames or because of IP or confidentiality or for whatever reason they don't want to be disclosing things. So we have different commercial access models available. So the simplest one is you come to me and say, Rob, I need 2 days of synchrotron time. Okay, great. We'll produce a quote and we'll knock the job out for you. But we can also work with you when you're going for funding applications or starting a new project at looking at collaborative models where it's a longer term engagement, you need more complex things from us, you need more input from our experts. And we've found that getting involved in that early stage is where you're a project inception can really help figure out, okay, this is where ANSTO can help you with this bit, or have you thought about it in this way? And we've had some really good results using that collaboration model. Either way, you still get the benefit of our experts assisting you understanding what it is that we do, because we know that you guys are not necessarily going to be the technical experts on everything that's sitting behind the fence. That's our job. You come to us with a business question and we'll turn it into a science question and a measurement. And to do that, here's my contact information. I had some brochures on the seats here. If you didn't get one and you want one, let me know and I'll let you know where to find it. So really thank you very much for your attention today. Do we have time for questions, or how do you want to handle that? One or two, if I can hear you. Got a microphone? Fantastic.
So we got a couple of questions. Anyone any questions?
Or see me after as well is fine. I'll be here for a little while.
No questions at all.
Fantastic. That
that's
obviously
easy.
means I've explained everything perfectly.
Please put your hands together for Dr. Robert, or his Italian friends call him Dr. Roberto.